right, today we're going to take a look at section 9.1, which is how probabilities are determined. And the first thing we're going to talk about is the way in which probabilities arise. So probabilities arise from experiments, and experiments are simply activities whose results can be observed and reported. So this might be a scientific experiment. It might be simply an experiment of, for instance, rolling a dice, and these kinds of ideas of rolling a die or flipping a coin. We could even have experiments in practical senses, such as if I were to guess the gender of my child, if I were pregnant, that kind of thing. Now the outcome is each possible result of an experiment. So there is one outcome if I'm pregnant of having a boy, and there is another outcome when I'm pregnant of having a girl. The sample space is actually just the set, the collection that is, of all possible outcomes for an experiment. So this, with my example I'm creating now, would be the example of boy or girl, and that would be inside of a curly brace. It would be a set. Now, an event is any subset of the sample space. So I didn't give a very good example that allows this event sort of description to talk, but let's go back to my rolling my die. So if I roll a die, one outcome is the number 1. The sample space would be the numbers 1 through 6, just the whole numbers. And then an event might be the even rolls, or rolls that are multiples of 3, or something like that. That would be an event. It's a subset, a smaller collection of the set we were talking about. All right, so the first theorem, 9.1, is the law of large numbers. This is Bernoulli's theorem. And it says the following: if an experiment is repeated a large number of times, then the probability approaches a fixed number. And that is actually found by taking the number of ways that your outcome, A, can happen, and dividing it by the number of items in your sample space. So the probability of A is n of A, number of items in your outcome, or different outcomes for your event, divided by the number of items in your sample space, n of S. Now, events that have nothing in common are events that are mutually exclusive. That is the, so this is the set notation. A intersect B is the empty set. It's a set with nothing in it. So if we talked about rolling our die, we could talk about rolling an even number and rolling a 5. Those are two different events. They have nothing in common. They're mutually exclusive. All right, so Theorem 9.2 says that if you have an event A and you have the sample space, that the probability of your event is somewhere between 0 and 1. 0 would be something like a 0% chance that it would happen, whereas 1 would represent a 100% chance that that would happen. And of course, this is a good time to discuss the idea that we can't talk about being something like 110% sure that I'm going to get an A on this test. There's no such thing as a possibility of 110%, in the same way that there's no probabilities that are over the number 1. All right, so Theorem 9.3 says that the probabilities of the events are equal to the sum of the disjoint outcomes making up the event. So for instance, if you were rolling a 6-sided die and you want to know what's the probability of rolling an even, well, I could count the even numbers and divide it by the 6, okay, so 3 over 6, or I could find the probability of rolling a 2, which is 1 out of 6, plus the probability of rolling a 4, which is another 1 out of 6, and the probability of rolling a 6, which is 1 out of 6, and I could add up 1 out of 6, 1 out of 6, 1 out of 6, and again I get 3 out of 6, which I would reduce. All right, so if we have mutually exclusive events, though, Theorem 9.4 tells us that the probability of the union, that is one event or the other happening, is simply the probability of one event plus the probability of another event. And that only works if they're mutually exclusive, right? Having nothing in common. So if I did again my example of rolling an even versus rolling a 5, well, the number of ways I can get an even is 3 out of 6. The number of ways I get a 5 is 1 out of 6. So this would be 4 out of 6 because there is nothing in common between the two sets. All right, then we have Theorem 9.5, and Theorem 9.5 says if A is an event, and we have several formulas we're going to write down, then the probability of A plus the probability of A bar, and remember A bar, and this textbook talks about the complement of A, so that's everything that's not in A. This probability is actually equal to 1 when we add these. Or we could write this as the probability of A is 1 minus the probability of A complement, or the probability of A complement is 1 minus the probability of A. These are just different algebraic ways to think about this. Again, A bar is the complement of A. That is all outcomes not in A. For instance, the complement of rolling an even would be rolling an odd on a dice. The complement of flipping a coin and getting heads would be getting tails on that flip. Now we're going to put together a list of all of our different probability theorems and properties. So the first one is that if you have the empty set, the set with nothing in it, that is going to give you a probability of 0. In other words, what's the probability that I go home and my husband's there today? Well, it isn't going to happen because I know where he's going to be today. He's in Norman. So he's not going to be at home when I arrive there. So this is an impossible event. For whatever reason, it's an event that can't happen. If you take the probability of S, where S is your sample space, that is a 1. This is a certain event. Okay? So the probability that when I roll a die, I get a number 1 through 6 is 1. I will definitely get some number between 1 and 6 when I roll a regular 6-sided die. For any event, however, any event A, the probability is somewhere between 1 and 0. So this is for any event A. Now, we just a moment ago wrote that if A intersect B is the empty set, then the probability of A union B is the probability of A plus the probability of B. This is for any events. A and B. Now, just in general, however, the probability of A union B is actually the probability of A plus the probability of B minus the probability of the intersection. So you should hopefully be able to see pretty quickly that obviously from step 4 that if the intersection were nothing from step 1, that tells us its probability would be 0. So this ending probability of A intersect B would not be there. That's how number 4 comes about. But the idea with number 5 would be something like this. So let's say I have one event that's rolling evens on my die, 1 through 6. So I've got 2, 4, 6. And I've got a probability of rolling a multiple of 3. Well, the problem is that a multiple of 3 would be rolling a 3 or a 6, which means I counted that rolling a 6 when I counted the evens, and I counted that rolling a 6 when I counted the multiples of 3. I double counted it. So I have to remove the double counts, and that's what this removing of this probability at the end is doing. It's removing my double counts. And so again, this is for any events A and B. All right, the number 6 was the other one that we talked about on the previous slide. If you have the probability of A complement, this is found by doing 1 minus the probability of A, or any other version of that formula that you like. And this is, again, for any event A. All right, the next thing I want to talk about is an example of all of this probability stuff with cards. So a reminder about cards. So in a deck of cards, the standard deck has 52 cards. Half of them, namely 26 of them, are black, and the other half, 26, are red. There are 4 suits of cards. There are hearts and diamonds. So there's 13 of each of those. Those are red cards. And then there are spades and clubs. And spades and clubs are both black cards. So there's 13 of each of those for a total of the 26 black cards. Now within each suit itself, there are different kinds of cards. Some cards are number cards. We have number cards that start at 2 and go up to 10. So you have a 2 through 10 that have numbers on them. We also have cards that are face cards. Those face cards are jacks, queens, and kings. And we have 4 of each of them because there's 1 of each suit. So there's 4 jacks, 4 queens, 4 kings. And there's also 4 of every number card, right? 4 8s and 4 2s and 4 7s and so forth. And then we have one card that is neither a face card nor a number card, and that card is an ace. Most games that you play consider ace to be a high card. That is, it is better than a king. But it's still not a face card. We don't consider that a face card. So this example wants us to consider drawing a single card from a standard deck of cards and determining which of the following events are equally likely. So a face card, we can actually think about a face card. There are 4 face cards in every suit, which means, and I have, 3 face cards in every suit, and there are 4 suits, which means I have 3 times 4 or 12 out of 52 face cards. Or you could reduce this to 3 out of 13. That is, in every suit there are 3 cards, in every suit there are 13 cards total. 3 face cards versus 13 cards total. So this is my face card. My not a face card. Well, that would include number cards, and it would include the aces. So it actually would include everything that wasn't those 12, which is 40 out of 52, or 10 out of 13. And so as you can see, obviously 12 out of 52 and 4 out of 52, or 3 out of 13 and 10 out of 13 are not equal probabilities, so these are not equally likely. All right, the second one is clubs, diamonds, hearts, and spades. So we actually have 1/4 of the deck that's clubs, 1/4 is diamonds, 1/4 is hearts, and 1/4 is spades. Or if you had preferred, you could have written each of those as 13 out of 52 because there's 13 cards out of 52 total. No matter how you write them, you recognize that they are all the same number, so these are equally likely events. All right, black versus red. Again, I could talk about the number of cards. We'll do that first this time. There are 26 blacks out of 52 cards. There are 26 reds out of 52 cards. They're the same. Or you consider that half of the deck is black and half of the deck is red. So these events are equally likely. All right, last one, part D. A king, well, there are 4 out of 52 cards that are kings. There are 4 out of 52 cards that are queens. 4 out of 52 that are jacks. 4 out of 52 are aces. So far so good. If the problem stopped there, these would be equally likely events. However, then we move on to even cards. And there are, in fact, in a deck, many more than this even cards. In every suit, we have a 2, a 4, a 6, an 8, and a 10. That is, we have 5 even cards. So we have, in each suit, and there's 4 suits, so there are 20 even cards in the deck. And then there's odd cards. So you might think, oh, well, there's probably 20 odd cards too, but you have to be careful because our odd cards actually start with 3. So we have 3, 5, 7, and 9. We only have 4 odd cards in each suit, so 4 times 4 suits would be 16 odd cards. Again, we can reduce all of these pretty quickly. This is 1 out of 13, 1 out of 13, 1 out of 13, 1 out of 13. This was 5 out of 13, and this would be 4 out of 13. From either perspective, we see pretty quickly that these are not equally likely events. All right, example 2. A civ class is comprised of 21 men and 35 women. So really quickly right now we can tell that there are 45 people in the class. There are 22 education majors, 13 religion majors, 12 science majors, 3 math majors, and 5 English majors. So if we assume that no one has a double major among these things, and a single student is chosen at random, we want to find the probability that this student is the following. So the first one is a female. So, as you see, there are 34 out of 45 people. Oh, sorry, it's 55. That's a mistake. Let me fix that. 55. There we go. Out of 55 people that are female. And 34 has factors of 2 and 17, and 2 and 17 don't divide 55, so that is reduced. Science majors. There are 12 science majors out of my 55 majors total. This also does not reduce. If we have an English major or a religion major, because these two can't double count, that is, there are not double majors, we can actually add these together. So the English majors are 5, the religion majors are 13, and 5 and 13 is 18. So there are 18 out of 55 that are either a science or a religion major. The last one says neither a math major nor a science major. So we can actually count up. There are 3 math majors and there are 12 science majors, which means there are 15 of these majors. Sorry, let me not write it there because that's not exactly what I mean. There are 15 of these that are majoring in either math or science, and we want them to be majoring not in math or science. So if you take a look, that means then that there are 40, get the right number written down, 40 out of 55 that are not majoring in either math nor science. And if we reduce this, we get 8 out of 11. We divide them both by 5. So there are 8 out of 11 probability of selecting someone who is not math or science. All right, let's take a look at example 3. A student claims that if a fair coin is tossed and comes up heads 5 times in a row, then according to the law of large numbers, the probability of tails on the next toss is greater than the probability of heads. What is your reply? Well, we've got a couple of issues here. The first issue has to do with the fact that he's citing the law of large numbers. Not know about you, but 5 times in a row doesn't really classify as a large number. So the law of large numbers, it actually tells us about what happens on average over time. And that means over a large number of experiments. It doesn't tell us anything about what happens on a particular trial. So this is not on a single one experiment. In this problem, this situation, we'll say, each toss is independent. Independent means it doesn't have any bearing or weight on what happens to the next toss. Each toss is considered all by itself, and it's not affected by tosses before it or after it. Each toss is independent with a probability of 1/2, because we can either toss heads or tails. So the law of large numbers doesn't speak to this issue really at all. All right, example 4, our last example. Example 4 talks about the spinner, which is a circle spinner, and it has 4 different pieces of it. But as you notice, the areas are somewhat lopsided. That is, our spinner is not sort of located in the center of the circle. So the following spinner is spun 100 times. Joe claims, again from the law of large numbers issue, even though 100 may not be considered large, but it's quite a few times, that the number of 4 should occur most frequently, most often, because it has the greatest area of the spinner. What would you tell Joe about his conjecture, and what is the probability that 4 will occur on any spin? All right, so the issue here is that the spinning is actually unrelated to the area The area of the circle consumed or labeled by a value. Instead, it is related to the angle the spinner passes through. And in this problem, each angle in our spinner is 90 degrees. Hence, all values are equally likely and there is a probability of 1/4 of landing on any specific value. And that is the end of our section 9.1.